Hola, ¿qué tal? Hola, Juan Ford, and hola, Maisha. And oh, wait, oh, I actually didn't. Oh, sure. I'm willing to. I have to admit, I have. Okay, I'm just gonna say hi to Newell. Well, you're way ahead of me, Maisha. You're ahead of me apparently. Because I'm the worst. Hello, I mean, hi, Lizzie. Um, okay, fair enough. Well, you're still ahead of me, and I'm not even gonna. Yes, I'm. Um, if I. Oh, that's good. Oh, happy birthday, Lizzie. Wait, today. What? The ninth? Oh my God. Um, happy birthday. Yeah, I did not know that. So your birthday is the day after Mother's Day. That's going to be interesting. Someday. That's like Mary having the same birthday as Christmas or so. Anyway, okay. Um, um, um. Oh God. Okay. I'm a mess even more than usual. I'm just going to say that we're yeah. Wow, Lizzie. I like that math. It's on Mother's Day every 11. That is fascinating. I got to think about that. I mean, I'm sure you're right. I mean, I got to think about that's really interesting. Okay. And I'm totally not asking how old you are. Um, more people here. Hold on, sorry. Every 11 years. That is really interesting. Wait, why can't I get these people? Sorry. What's going on? Oh, okay, here we go. Okay. Okay, that's funny. I'm going to stay out of that. Okay. I know we have okay, you are a direct chat person. You're way ahead of me. Look, you're a much better person than I am. You guys, so the things are still dribbling back really slowly. I don't know what it's pathetic. I'm pathetic. I humble myself. Well, I don't even know what the word is. I, the midterms are coming back very slowly. You're getting them. You have them. Some of you don't. Most of you don't. They're just coming one by one. I don't know why. I it's not, but I will say that the same thing with the extra points assignment, those are coming back faster, but a lot of you in this section still don't have them back. But I'm telling you right now, if you did that extra assignment about fields, and if you turned it in on time or talked to me, if you turned it on time and you actually attempted both questions, you have stuff written that takes up more than like a page, then you're getting the 14 points. I promise you that. I'm going through those. So that's very nice. And it will all come out in the wash, and I still feel terrible, and somehow I'm just getting worse, not better. I mean, with where I should be with those things, but that's the reality. Also, I didn't even put a game turn in yet today. I'm gonna pause for a second and put a game turn in, but we're just gonna move on with them. And I know the clock is super running out on everything. Believe me, I know. And we're gonna talk about that on Wednesday, about the end of the semester and all that and grades. But right now, I'm just gonna move on with the material. Please forgive me. And if we turn out to find out how old Lizzie is, then we do it. If we don't, we don't. It so okay, but here we go. We're gonna right here that goes. So we're gonna keep talking about fields today. Oh, and one thing I did see in the extra point thing that you handed in, or the ones that I've seen so far, I do actually think that you get what's going on computationally with fields, which is good, which is very good. Now we're going to keep going with fields. Fields is like where the course ends, or the last topic of the course. I'm going to keep talking about fields today, but we're going to talk about them in a more visual way rather than a computational way. So it's a little bit of a left turn. We're going to talk about something called field lines today. You'll see. Bear with me for 1 second though, because I do have to put the game turn in. So so please just talk amongst yourselves for a second, or talk to Lizzie about her birthday. Hold on one, or give her, I don't know what. Just bear with me for 1 second. As I say, just bear with me for a second. I'm sorry about this. Actually, well, here, I'll give you the next page so that you can start copying. All right, if you can, I just turned the page of notes on the thing. This is what we're going to talk about today. I'll read my handwriting out in a second, but maybe you can start trying to take notes on this. Let me just bear with me for a second, as I say. Okay, thank you for your indulgence. Okay, oh, let me look in the chat if I'm missing something. Oh, that's funny. Okay, wait. I know the answer to John. So no, John, the answer to you is no. Sorry, soon. I don't know what to say. I'm just embarrassed. Not just embarrassed, I'm also contrite. But all right, I'm gonna go on. No, I'm not. I appreciate you're very kind. You are a far better person than I am. There's no question. But you're also really paying attention that you even heard me muttering like that to you just now. Wow. Okay. All right. No. So, and look, it's almost as hard for me to teach when I haven't returned these as it is for you to learn. Like, in the sense, I know it's like painful and torturous to pay attention when you don't have resolution on grade numbers. I can't change that fact, but I do understand it. So I commend anybody who's able to pay attention at all today. I know it gets harder and harder as we get closer to the end, but I think you guys have been doing a great job so far. And I'm just going to go on because there's not, I don't want to let one error get me too, so to speak. Right. So here's the deal. So we're still talking about fields. And we're going to talk about how to visually represent, and we're going to talk about a visual representation, a tool for communicating fields. A tool, we're going to talk about a tool that's used to visualize, represent fields that's much like vectors or much like even graphs, in the sense that, let's remember, now I know some of us love graphs, some of us hate graphs, most of us probably still hate graphs. I hated graphs until I liked them at all, and then I started loving them. The thing about graphs and the thing about vectors is, or free body diagrams for that matter, like the thing about, or circuit diagrams, the thing about proper scientific diagrams, right? The good and the bad of them is that when we do them properly, like when we draw them carefully or have a computer render them or draw them with some sense of scale and precision, the thing about scientific diagrams, just to remind you or to reinforce, they're not just rough qualitative suggestions of what we think is going on. When we draw diagrams according to certain rules and certain conventions, we end up actually using the diagrams to convey precise quantitative information that we then use for computation, right? Like vectors properly drawn tip to tail to a certain scale, can actually be used to, for example, add vector quantities. And, if you measure precisely on a piece of paper and stuff, you can get answers to vector problems that you otherwise couldn't get. And so our pictures are like primitive calculators. I mean, they are when treated properly. It turns out that, and same thing with graphs, like graphs actually depict quantitative information in a manner that actually, they don't, in other words, pictures don't just reinforce what we're thinking, they actually do stuff in a precise way. And there's a way of depicting fields that is equally precise and important and ends up becoming as much a part of the language of fields as numerical or symbolic calculations or written English. And that's what I want to show you today. Now, first, I'm going to show you, to make this clear. Well, let me read what this page says here is, well, it says on the top, how to visually represent and compute fields. That's what it says in black on the top. Then in blue, it says first, it says first, I'm going to show you the less standard option. Okay, and I'm not doing this by mistake or to confuse you or something, but first I'm going to show you an option called vector field diagrams. Whoa, hello. Okay. Okay. I didn't need to circle that. I meant to circle this. Okay, first I'm going to show you vector field diagrams. The thing depicted at the bottom of the page here in black is the vector field diagram for the electrostatic field for the E field due to a positive point source known as plus capital Q. Okay, so let me make it clear. This diagram at the bottom is not yet the ultimate thing that we want to do today. This is a type of diagram from which we construct or on which we build this slightly better notion called field line diagrams. This is a vector field diagram. So let me explain what's going on here. We're imagining that we have a point source of charge, like a positive point source of charge. So we have like a proton sitting on a lab table in the lab, or a proton somewhere in outer space sitting there. And we believe that this proton, this source of charge, this creator of force or of interaction or whatever, we believe that this point source is sitting there and it creates electrostatic field everywhere around it in space, right? And when we say that it creates electric field everywhere around it in space, what we're saying, what we imagine is that at any point in space, someone's here, sorry, hold on a second. Okay, any point in space that you choose, like at any known distance and in any known direction from our known point charge, we believe that in any location you test in space, if you were to imagine or hypothesize or in your mind place a 1 coulomb of positive hypothetical test charge, we imagine that if you placed 1 positive coulomb of test charge anywhere in space, that it would feel a force from the source, right? Like a force is something that one object does to another. So we imagine that if you placed a second object somewhere in space, it would feel a force from the first object, an electrostatic force. That force, being a vector quantity, would either push or pull. It would point in some direction and it would be of a certain strength. It could be measured in a certain number of newtons, right? So what we're doing is we're drawing a little arrow, we're drawing a little representative vector at representative points in space to say this arrow in this picture, in this vector field diagram, we draw a arrow at representative points in space depicting the magnitude and the comparative direction and magnitude of force that would be experienced by 1 coulomb of positive test charge if it were to be found at that location, right? So so that's what these arrows are trying to tell us. What would be the force that would be experienced by 1 coulomb of positive charge placed at those locations due to the positive Q that is sitting there at the source, creating this field, creating this force waiting to happen. So what it says in red on the sheet, like, so what you have here is this positive Q, and you've got these arrows radiating out from it, arrows that are drawn along radial lines and are getting deliberately smaller and smaller as we get farther and farther away from the charge. What it says in red, and you can barely read it, is it says, like, it has these little points, like a little dot in red, and it says next to it like P1, like as in 0.1, as in location that we can imagine number 1. And then there's another point like P2, another location that's a little farther away that we can imagine. And those are just like arbitrary locations that we're interested in what's going on at those locations due to the positive Q point source. And what it says in red is that P1 and P2 or P is some point in space. And the vector at that point in space, the black arrow at that point of space that we're looking at, shows the magnitude and direction of the force that would act on a +1 coulomb test charge if there were a charge there, that's what it would experience. So, I mean, okay, as always in physics, some of you I lost long ago, minutes ago, because it's so confusing and annoying or boring. And some of you I lost minutes ago because you knew exactly what I was going to say, like from sentence 1, and now I'm just repeating myself. I don't know. I'm either talking to everybody or I'm talking to nobody. But what I'm trying to say is each one of these arrows shows how you would be pushed by the plus Q source. It shows in what direction you would be pushed if you were a little proton somewhere in the space. And it shows how hard you would be pushed. Notice that the length of the arrow represents the strength of the force. The farther away we're getting from plus Q, the smaller the arrows, deliberately, because KQQ over R squared is what is equal to the electrostatic force. The greater the R, the smaller the whole action at a distance, right? So this is great. That's a perfect, wow. Okay, just in the nick of time, that is a perfect question. And here's the answer. So John asked, what about like negatives? What about electrons? Perfect question. Here is the vector field. I really am thrilled that you just asked that. And thank you for paying attention again. This is the vector field diagram due to a negative point source. Now, it really is a great question. And so note a couple of things about this, right? So the first page was positive. This is negative. A couple of things I want to say. First of all, true of both pictures, you note what it says on the bottom in red, in blue. It says, note, representative arrows are drawn until we see a pattern. In other words, the whole idea is I've drawn just enough arrows so that we can sort of see the trend or see what's happening with the force. And what do we see here in this pattern? We see that a negative point source would pull in, and I'll explain that in a second. And we see the thing I said a moment ago, that the farther away you get, the less intensely you would be pulled in, right? So we're just drawing representative arrows. Like the idea is even that point P isn't that red point P, that location that I'm interested in. Some people would call it a location of interest. Some people would call it a field point. That point P is not literally drawn right on an arrow, or there isn't an arrow literally drawn on it. But the idea is that, yes, right. So let me just say this and then I'm going to get John's thing. But the idea is we draw just enough arrows to see the pattern. We assume that arrows actually are everywhere and go on everywhere. Like those arrows get smaller and smaller until maybe my marker is too thick to draw one or my hand is too coarse to draw one. But we do assume that there, no matter how far away you get, there is some force acting with some number of newtons, even if it's a very small number of newtons. Two more quick things, and then I want to get John's next question. But so just note, these are representative arrows, but notice I drew enough to see a pattern. I'm trying to, even though I'm sketching them, if I were doing this with a computer, I would do it a little bit more precisely. And either way, what I'm trying to do is obey some sense of consistent scale. Like in each case, I've decided to draw like 8 arrows coming into the 8 original arrows in the inner circle coming into the charge. Maybe I'm drawing 8 arrows because maybe this charge is an 8 Coulomb negative charge, maybe, right? And maybe if it had been a smaller charge, maybe I'd only draw 4. Or maybe if it was a bigger charge, like a 16 Coulomb charge, maybe I would draw 16. So I can pick the number that I'm going to draw sort of to establish a scale and to establish a scale. But then once I make that choice, then I stay consistent with that choice and I draw everything as symmetrically as possible so that I can see the pattern. That's number one. But then I want to talk more about this negative and positive thing, but let me see John's second question because it may be, oh, great, Elizabeth. Wait, okay, so I'm going to go back and see. I know John had a second question tucked in there that I missed. I'm going to see. But what Elizabeth with an S just said is like told. John's question was great, and I'm seriously excited. And Elizabeth L, her answer is great. So great that, of course, I'm going to bore everybody and repeat it, even though you probably get it the minute she says that. But yeah, I mean, the answer is yes to what Elizabeth's saying. Let me drag that out in a minute. Because literally that escaped me for a year of college. Like I didn't get that for a year. So, but hold on, let me just see. So I get pushed back. Oh, and sorry. And that's echoed with what John's saying in the second. Okay, you guys are totally on this. You know, and no joke, no, Okay. And great question. So let me back up. No, it is absolutely true that, no, that's fine. Well, she didn't. Okay, so let me say to everybody, because this is a subtle, John and Elizabeth are correct, but that doesn't mean what they're saying is obvious. And literally what they're saying, I mean, I remember it escaped my understanding for sophomore year of college. I didn't get it at all. And I didn't know I didn't get it. So things totally confused me junior year of college. Like in retrospect, remember this being a big problem for me. But I didn't know that it was a problem. I knew I had problems, you can imagine. But so let me spell out for a second what Maisha's asking, what Elizabeth and John are saying. What we're saying is this: source charges. Well, yes. Okay. Wait. Well, kind of. Wait. So the last part that John's saying is speculative. It's a good conjecture. I'm not sure I'm going to totally agree with the more math thing, but okay, let me say, but still, we're on the right track here. Here's the point. We're looking at, okay, I'll say it concretely first. Source charges can be positive or negative. Source charges are whatever they are. Like this page, we're using vectors to depict what the field would be that would be created by a negative source. And on the page before, on this page, we're drawing arrows that would depict what would be created by a positive source. Notice these arrows here created by a positive source push out, and that will always be true. And these arrows here created by a negative source are all identical, except they're all pulling in. The reason for that, wait, no, this isn't, wait. No, well, I mean, wait, that's a good question. The drawing the whole picture thing is new. I'm starting this topic today, the drawing the pictures. The concept of what we're drawing is an old topic. And I think what I'm about to say, well, you'll tell me, I'll say this, and then you tell me if it seems new or old to you. Because I kind of think here's what I'm trying to say. That someone's here. Oh, I thought she was already here. Okay. I'm saying, wait. Yes, the thing that Elizabeth with an S just wrote into the chat. Oh yeah, you might have missed. Okay, yeah, you might have missed something that's important to this. That is, possible. So let me, and the thing is, what Elizabeth is saying is right. Wait, dental. Oh, that's why I was like, wait, what does that have to do with dental? I don't even know how to draw the field line of a dental surgeon. But right. Okay. No, and I'm not like blaming anybody for missing class. Right. Okay. So, but okay. Thank you. I think the main wisdom that's happening, the most wise thing that's being said right now, in a way, is, well, I don't want to play, is kind of what Elizabeth's saying, and also what John said earlier. Here's the deal. We're trying to ask the question, what would a charge do to the universe? What influence what would a charge do to space? And we're trying to come up with, and we have this concept of field, like charges push or pull other charges. Charges push or pull other charges. That's called a force. But the way we now talk about it, that I guess sort of did happen last week, I guess, when Maisha wasn't here, or maybe other people weren't here, is we're saying when it comes to forces that act at a distance, okay, just stop for a second, please. This is like hard enough. Wait, this is about electrostatic fields. Hold on. So everything we're talking about right now is about electric fields, electrostatic fields, which I actually do kind of think we started a couple of weeks ago, but we got more into last week, I suppose. So let me just say, everybody take a pause for a second, because the problem also is that sometimes I'm not totally sure I can tell the difference between the jokes and the serious thing. I'm saying protons push and pull other protons and electrons through electrostatic forces, KQQ over R squared. But because they happen at a distance, because they happen through empty space, the pushes and pulls happen without touching, just like gravity happens through empty space without anything touching. We discover, or we invent, just stop for a second. Wait, please, wait. Okay, we discover or invent this notion, okay, thank you, of fields with gravity and electricity, and yes, ultimately with magnetism, but we're not up to magnetism yet. I haven't said anything about magnetism yet, but yes, with the gravitation between masses and the electrostatic interaction among charges, instead of just saying a proton just pulls an electron, or a proton pushes another proton, or instead of saying the sun pulls the earth, what we actually say is the sun creates a gravitational field everywhere in space, and then if the earth is some object, some mass that's located somewhere in space, then it's in the sun's field. So the field pulls the earth. The field exerts a force on earth. We say in it, yes, yeah, right, good. This is much like, and it's not a coincidence. I mean, you're not crazy, man. That's why it's in the same class. That's right. Just like for sound waves to travel from my mouth to your ears, we've said first there has to be something in between, something generally like air, but maybe sometimes like water or something that we call the medium. We say that sound are ripples, are pulses, are oscillations traveling from my mouth to your ears. But for oscillations to travel from my mouth to your ears, there's got to be something in between my mouth and your ears oscillating. And that thing that's in between, which is generally air, we call the medium. Okay, good connection. Medium is to waves, in a way, as fields are to fundamental forces. And by fundamental, I mean gravity and electricity, and yes, ultimately magnetism. So I'm saying, first of all, I mean, the quick summary of all of last week or whatever is, from here on in, instead of saying that a proton just pulls an electron, we say a proton instead of saying that a proton exerts an electrostatic force on an electron, because it's very hard to picture how that works in empty space, especially if that force is based on specific numbers, like where the proton is and where the electron is. And that force apparently will change if either the proton or the electron change their location in space. Like if R is changed, then the whole F is changed. And it's very hard for us to understand or picture or measure or predict how these forces can change in accordance with these changing bits of information unless there's something in between the two objects holding and conveying and transmitting the information. And by information, I mean like how big these charges are and where they are. So we say, I mean, that's literally like the summary of all of last week. Whenever it comes to forces that happen at a distance through empty space, we don't just say there's just a force. We go a step further and say, no, there's a field between the two objects. We say that the minute the proton exists, it creates a field everywhere. Like it somehow deposits the vital stats, the information describing how big it is and where it is. It deposits that information everywhere in space somehow. And if something else, or when something else exists in space, like an electron, the electron feels the force from that field in space. Wait, so, yeah, oh, that's a great question. It's a very deep question. I will answer it in a little more detail right at the end of the class, but yet the answer to both my Ishas, and these are great questions. I mean, as long as they're serious. I mean, and it might seem to other people that I'm getting off the topic, but no, this is the topic. What Maisha, and I will get back to the positive negative thing in a second, but what Maisha and John are saying, when Maisha says, can space act as the medium, like as in outer space when there's no air, or does there need to be something extra there? Right, okay. And then John says, is the field for every proton covering all of space? So the answer to both of those questions is yes and yes. What I mean is this. I mean, great questions, and yes are the answers. What I mean is the minute you put a proton in space, it deposits somehow. And of course, this leads into other mysteries and intrigues and fact, but somehow the proton deposits the information describing its size and its whereabouts, its location, everywhere in space. So first of all, right, to my interesting, there doesn't need to be anything else in space for this to happen. The information itself gets deposited into space, and the information itself is what we call the field. I mean, in other words, right, the field is the medium for this information transmission or communication, and there doesn't need to be anything else in space for this to happen. There does not need to be air or heat or gas or something. In raw space, this evidently happens. The information itself becomes a medium or a thing in space. And good question, Zhao. Yes, Q does stand for proton or charge, and in this case, yes, Q does stand for charge. If it's positive, it's a proton. If it's negative, it's an electron. So yes, but then back now to John's question, and then back to the other question. John's question: is the field for every proton covering all of space? Yes. Like the minute there's a proton in space, the information describing that proton, or the minute there's any charge in space, like one proton, two protons, three jammed together, the number of protons that it is and where it is somehow existing everywhere in all of space. Yes. And that information describing the source charge, that information itself is what we call the field. Now, a couple more things about that to get back originally to Elizabeth's thing and other people. But these are great questions. I mean, if I can answer all these, we can still get to, and we can, then great. What I'm trying to say is that any charge can create a field. A positive charge can create a field. A negative charge creates a field. Field is the information in space that's telling what kind of force would be exerted at a given location in space if we found a charge there at that point in space ready to receive the force. In other words, the field is the information. It's there. Even if there's just one proton in the whole universe and there's nothing else in the universe, there's one. It creates a field everywhere in the universe, like John's saying. It places somehow its information everywhere in the universe. And it's not a force yet, it's just information. It's just information that basically says how strong the force would be and in what direction it would act. So then the idea is, if we were to place a positive charge of 1 coulomb somewhere in space, we would call that charge the test charge, to see what would happen. That 1 coulomb of positive test charge would be pulled or pushed in a certain way and with a certain strength. Whatever would happen to, and that would be a force, right? Once there's a second charge somewhere in space, the charge that we would call the test charge, then we would actually, based on that information that the charge is sitting in, it would experience a certain amount of force. Before the charge is even there, before the force even actually occurs, we call this information the field. The field is like a prediction in a way, or a calculational tool. The field is the force that will happen or would happen if a positive coulomb of test charge were placed at a location. So just, I know there's tons happening in the charge. In the chat. I'm going to look in a second, but I really want to just reinforce the thing that Elizabeth said like 45 minutes ago. I want to say, in other words, if you're sort of following what I'm saying, you'll know you're following this if this thing I'm about to say makes sense to you. I'm saying then that the source of a field could be positive or negative. Like anything could make a field. A proton can make a field, an electron can make a field. So our diagrams could assume a positive source or a negative source. But what we're trying to depict, what the field is doing by agreement, by convention, by standard common methodology, we're asking ourselves, what would happen if a positive test charge were placed somewhere in space? What would happen to a positive test charge due to the source? The source can be positive or negative, but the test we're always assuming is positive. It's an assumption. Remember, the test charge isn't actually there. We're actually asking what's happening to space. But the way we're envisioning what's the force that would kick into reality, that would kick into gear if we actually imagined a positive charge at a certain location. We're really asking the question, what's happening at different locations? And we're testing it in our mind by saying, if we put a positive 1 coulomb here, how hard would it be pushed or pulled and in what direction? Or if we put a positive charge over there, if we put the positive charge in our mind at those red locations called point P, then the vector, the arrow that's drawn there, is trying to tell us what would happen to that hypothetical positive test charge. It's a hypothetical charge. It's just for testing in our mind. And we hypothetically assume in advance that it would be positive. Why? Now this gets to a John thing, and I know there's still tons in the chat. I will stop in a minute and get to the chat. This has been burning for like 15 minutes, so I just want to get to it. Why do we assume that the test charge is positive? Because we have to make one assumption or the other so that we all could be consistent. We could live in a world where we all assume the test charge was negative. There's nothing that would be wrong with that. We could do that. All of our diagrams would be flipped, but everything would work out consistently. We'd get answers. But we have to assume one or the other. If we don't know if the test is positive or negative, then we're not speaking the same language as one another. So by convention, we just adopt the idea that the test charge is always reckoned, is always assumed to be positive. Then, and I'm almost done with this, but I do think there was at least 4 people in the room that are very much, I think, hopefully about get this in a way that's better than if I just straight lectured. I'm saying then, if the source could be positive or negative, but we always, and the source is the creator of the force, the pusher or the puller, whereas the test, the receiver, always is assumed to be positive. Then if you think about it, it makes sense. Positive sources always push out, always. Positive sources we depict as pushing out because they would push out positive test charges, i.e. positives repel other positives. But negatives, next page, negatives are always drawn as pulling in because a negative would pull in a positive test charge. The source can be positive or negative. The test is always assumed to be positive. Therefore, our diagrams depict what would happen to a positive test. Therefore, we're always imagining positive sources as pushing out on space. And we're always imagining or hypothesizing or modeling negatives as pulling in on space, because we're imagining what would happen to positive recipients. Now, okay, so those are the two diagrams. Now, this is just all what I'm saying is like true. And in some sense, you might have already understood last week, to be honest, some of you, if you might have this might not be new information to some of you, except that what I'm trying to do now, and I'm going to look in the chat, I promise, I know things are happening in the chat. But I just want to tell you, like, this concept of field, the field is the information describing the size and the whereabouts of an original source. Like, you put some charge or some, and it doesn't have to be, you put some charge or some amount of charge, some shape of charge somewhere in the universe. That's now a source. It's going to create field. The field is the information everywhere describing how big that source was that you put and where you put it. And the reason the information is everywhere is that, or the reason we believe the information is everywhere is that then if some second object comes along and finds itself in the information, it gets the exact right information of how hard to be pulled or pushed. Sorry, I'm totally distracted. So what was my point? You might say, wait, this is very mysterious. Like, objects just like place information everywhere in the universe. Like, the minute a proton exists, information describing how big it is and where it is just goes everywhere in space. You might ask, how does that work? Like, what? Why would I believe that? I have to tell you two things. One, why we believe it is because it evidently seems to happen. Why we believe in these fields, remember, is because evidently objects do seem to pull and push each other through empty space in a manner that seems precisely quantitatively determined by this information that we're talking about. Somehow or other, as electrons get closer to protons, they get pulled harder by the protons, even though the protons aren't touching the electrons. The protons seem to know how far away the electrons are as they pull on them. I don't mean know consciously, but somehow the proton pulls on an electron, or the sun gravitationally pulls on the Earth with an exact amount of newtons that seems fully determined by how far away the Earth is. And as the Earth gets closer to the sun, or as an electron gets closer to a proton, the amount of the pull or the push seems to adjust accordingly. So somehow the information does seem to be contained in and transmitted through space. Like, how, really, why? I don't really know. Philosophically, but as a scientist, I seem to know, or I seem to observe, that these effects seem to occur. So the word for this very, very mysterious and beautiful and strange phenomenon, the word is field. I can't tell you why the universe allows fields to exist or how they came about into existence, but they seem to exist the same way. Just the gravitational force seems to exist. Things fall. Right? But now, if you want a better, and I'm about to shut up and look at the chat, but I'm here to tell you, the reason we believe in fields at all is because we see their effects. If you're asking, okay, fine, like, I guess I believe them, but I still know what you're talking about. Like, you're saying all this about information everywhere in the universe. Like, you're saying when a proton, Yaverbaum, or saying when a proton is sitting in a lab, it's plopping down, it's depositing the information of its whereabouts everywhere in the world. Like, I could believe you if you want to tell me that, Mr. Scientist, but I have no idea, like, even how to picture that in my mind, or like, even, I can't even get a grip on what you're saying. Yeah, like, you might be saying that. And by the way, that's totally how I felt when I was thinking it all in college. And here's what I'm here to say. I can't convince you of exactly what, I can't make you believe in something that you don't believe in, but I can certainly help you visualize what I'm talking about. What I'm here to do today, after I go back to the chat and back to my pages, is I'm here to say we have a way of visualizing, of modeling, of picturing this field thing that I'm talking about. We have a thing first called vector field diagrams, and then ultimately a thing called field line diagrams that we picture in our mind when we're trying to picture fields. Do we literally think fields are literal arrows that are literally sitting in space? No. I don't know what they literally are any more than you do, but I have a way of picturing the fields in space that allows me to help make predictions and calculations, just like I have a way of picturing gravity in space that I don't think is the ultimate answer or the ultimate explanation of everything, but it's a tool. So what I'm trying to get to in this class is how we can visualize, how we can actually picture and represent fields in our mind and on the page. And the more we picture them and represent them, the more we start getting comfortable with imagining that they're there or believing that they're there. So I want to get to, so I'm saying what you have so far is the vector field representation right here on this page of a negative point source. What you have here on the other page is a positive point source. And the idea behind the representation is you picture, when you're picturing a field for the moment, picture that at every point in space, there's a little arrow, not literally like a styrofoam arrow, but picture that at every point in space, there's a little arrow that points either toward or away from the source and is indicating, like if you were to put a little proton there, what direction the proton would be shoved, would be pushed or pulled, and how strongly. These arrows show direction, and notice that as they get farther and farther away from the charge, they get smaller and smaller, because the idea is that the length of each arrow represents the strength of the force that's waiting to happen. Okay, that's like what I'm saying so far. We're totally not done, but that's my overall like answer to the questions I saw so far in the chat, which I loved. Now I'm just going to take a breath and look at what more is in the chat. Okay. So I saw, right, John Ford, it's a charge. Okay, so if this is true, how does this relate to the heat? Whoa. Okay, so I'm looking at the chat. And so John asked a question about heat death of the universe. Great question. I love, if I'm not careful, sure, I could talk all day, sort of, about the whole notion of heat death of the universe. But I do have to admit, this doesn't really directly relate to that. Like, I'm not sure there's really, heat death has much more to do with the second law of thermodynamics, about the law of entropy and all that, which is fascinating. I love it. Like, we could talk, I'd love to talk in my office about all that. But this is more about electrostatic. Like, this is about fields. That's more about entropy. So just to be honest, this, wait, okay, I'm just trying to make sense of how this really, does this relate to the heat of the universe? Does that mean that protons will decay? Okay, I think I understand what that question is. I think that relates back to John's earlier question. Like, the one thing I could say to stay on topic a little bit is the assumption behind a field. The field is the physical or the visual representation of KQ over R squared, that whole idea, the force per charge. And so just like in the math, you can make R as big as you want, right? I'm saying this to everybody now. This is all about KQ. In fact, let me just, so that you don't think I'm totally off. Hold on a second. Okay, this whole idea is about how the field is directly proportional to charge, but gets weaker and weaker. Gets weaker and weaker in inverse proportion to the square of the distance we investigate away from the charge. So what I'm saying is R can be as big as we want. If R is huge, E is still not zero. The bigger R is, the smaller the field is, the weaker the field is. The farther away you get from the proton, for sure, the weaker the field. But there's no, you would have to go literally to infinity to measure or detect literally zero field. The field does extend as far as you can imagine R extending, if that makes sense. Like, there's no cutoff to this. So I don't know so there's no place that there's no field. Let me put it that way. And that also goes back to Maisha's question. Like, as long as we have space, and this also goes to John's earlier question, as long as we have space, we have field. The field extends everywhere in space. I don't know it because R can be as big as it wants and E still won't go to zero. I don't know if that totally answers that question, but I'm going to go on and look more. And there is more that I want to do today, of course, but let me just look more in the chat to see if I miss anything else. I mean, yeah, okay. So I should have seen that question was, it wasn't too crazy, but it is a little beyond the scope of this class. Yeah. Okay, wait. So the proton field. Oh, wait. Okay, so now Maisha's question. Okay, Maisha's question in the. I wish you could see the chat that I'm scrolling. But Maisha's question then she says, so if the proton field is theoretically all over the universe, is the reason why it actually isn't is because there are other protons resisting against it, or am I misunderstanding something? Right. Okay, that's good. I don't think Maisha is misunderstanding something there. Like I'm saying that every single charge creates a field, a force waiting to happen, a push in the case of protons waiting to happen, and a pull in the case of electrons waiting to happen. I am saying that, but yes, she's right. I'm saying that's true of every single charge in the universe. Also, by the way, every single mass in the universe, bit of mass, is creating a gravitational field everywhere in the universe. So, right. So the reason like I'm not attracted to the ceiling right now, the reason I'm not flying to the ceiling of my own apartment right now, or house or whatever, the reason I'm not just like flying to the ceiling is because as much as the ceiling is pulling on me, to be crude about it, the floor is also pulling down. Or the reason I'm not like flying to Jupiter right now, even though Jupiter's in front of the Earth, is because Mercury is behind the Earth also pulling me. I mean, those are both kind of extreme, stupid examples, but I'm saying like, yes, the reason we don't just, the reason one given proton doesn't just automatically get pushed in one given direction is because everything I'm saying is happening to all things at all times. And so a lot of cancellations are occurring. In fact, I'll say this much. The reason we tend to observe gravitational effects on a macroscopic level more than we tend to observe electrostatic effects is because all things are made up of atoms. Atoms are neutral for the most part. In every atom, there's an equal number of protons as there are electrons. So yes, anything I'm saying right now that's happening to the atom, to the proton that's at the tip of my nose, like the proton at the tip of my nose is pushing away on the proton on the tip of your nose. Like that's true. But it's also true that the electron in the tip of my nose is pulling on the proton in the tip of your nose, et cetera, et cetera. So most of these electrostatic pulls and pushes are balancing each other out as we speak in the macroscopic world. So we don't even really care about them or notice them until one of two things happen. Either a whole bunch of electrons accidentally, temporarily get gathered in a small place until accidentally there's a net negative charge somewhere, as in what happens when socks rub against each other for too long, or a balloon rubs against my hair for too long, and some of the electrons in the outside in the orbitals of atoms get ripped off, and some atoms get temporarily ionized, and you suddenly have a clump of extra electrons somewhere. Then you get a momentary repulsion between that little clump of electrons like in my hair and the clump of electrons like in the balloon or something. You get a momentary disequilibrium, and there will be a pull or a push or something like that, and a jump so that the electrons will jump to the protons that are attracting them in the balloon or whatever. And that's that little spark or that little piece of lightning that we get. And of course, this also happens between the Earth's surface and clouds. Like temporarily, occasionally, we get these asymmetric distributions of net charge for the sole reason that electrons can be dislodged from atoms because they're way out there in the orbitals, right? So they can get dislodged and start traveling as free electrons. So occasionally we get these disruptions where we can see for a moment things realigning, where we can see an electrostatic pull or push until everything gets realigned and the electrons go back to where they want to go, and then everything gets neutralized again, right? Or we go through great pains to create these situations in little voltaic cells that we now call batteries. And then we make circuits, as you did in the lab for many challenging weeks, right? Like electrostatic pulls and pushes are happening all the time, but mostly they're neutralizing each other until we either freakishly have a momentary asymmetry, or we deliberately create an asymmetry, and that's called a circuit, right? So, but yes, it's happening all the time, but mostly they're canceling each other out. And similar arguments can be made about gravity. Okay, I'm going to go back to the, but these are great questions. And I do want to, I may have to pause on the, wait. Oh, okay. Now Elizabeth LaFontaine's question, who's rocking today? Well, everybody's rocking today, but Elizabeth, your question, she says, this may be a dumb question, but does this relate to the moon's effect on the tides? Not a dumb question at all. First of all, no, it's not a dumb question. Here's the fast answer. Everything I'm saying about gravitational pull absolutely is describing the moon's effect on our tides. Not a dumb question at all. The tides are one of the reasons that we believe that objects at far distances can pull on other objects at far distances through empty space without touching. We believe that the moon pulls on the earth gravitationally. Now I'm talking, right? We believe that the mass, and in fact, this is the moons and the tides and all that was one of the things that led Galileo and Newton to really start putting some confidence and some effort into this whole idea of universal gravitation, well, particularly Newton. And no, it's a great question. I'm going to quickly answer it. I mean, I guess today is that kind of class. The moon is a big mass. It's got some M. The Earth is a big mass. It's got some M, M1, M2. They're separated by a distance R, like a distance R. Put R squared in the denominator, multiply out the numbers, and you get a certain force that the moon is pulling on the Earth. Here's the thing, though. First of all, most of the surface of the Earth is water. So mostly what the moon is pulling on when it pulls on the Earth is the water on the surface of the Earth. But better, more specific point. I'm saying this is a great question because maybe it'll make some things clear to some of these other questions. I'm saying over and over again that the gravitational pull, just like the electrostatic pull or push, is inversely proportionate to R squared. In other words, these forces that I'm talking about, like today we're in the class right now, we're really talking about electricity, but I'm trying to say that electricity works mathematically and physically just like gravity. So it's not a dumb question, as long as you understand that the attraction between the moon and the Earth is a gravitational one between the two masses. It's not an electrostatic one because, again, I mean, there are electrons in the moon pushing on the electrons in the Earth, sure, but there's an equal number of protons in the moon pulling the electrons in the Earth and vice versa. So the electrostatics basically balance themselves out. But with the gravity is always a pull, never a push. And it's based on R squared, just like electrostatics. So everybody check this out. This might put some things in focus for you, Elizabeth's question here. I'm saying, here's the moon. Oh, you can't, sorry. Okay, like here's the moon. My non-ring finger is the moon and my ring finger is the Earth, right? So the moon is pulling on the water surrounding the surface of the Earth. Okay, sure. But look, it's pulling on the water on this edge of the Earth, the edge that's closer to the moon, but it's also pulling on the water that's on the other side of the Earth, right? Like the moon is pulling on all that water. It's pulling on the closer water more strongly, GMM over R squared, GMM divided by R squared. So the water that's closer has a smaller R. The moon is pulling on it a lot. The water back here that the moon is also pulling on is not pulling on it so hard because it's a bigger R. So it's pulling more on the water closer to the moon. So that water gets yanked. Like, so if you picture this whole big sort of bubble-ish or like this big, whatever, what's like membrane of water around the Earth, it's being squashed, it's being yanked toward the moon and more so on one side than the other. So all the water sloshes to one side, high tide on that one side. But then a little bit later, the moon's going to be over here on the other side. So it's going to pull the water the other way. So that that's high tide on the other side, low tide on the first side. In other words, where the moon is in relation to the earth absolutely affects where the water, the oceans of the earth are sloshing, because they slosh toward the moon, and they slosh more at the closer they are to the moon. And that's all happening at a distance. So that's how gravity works. Now we're saying similar things happen with protons and electrons. And ultimately we're saying, to go back to the chat and back to the thing, because the actual amount that one thing pulls on another seems to be literally based on how big those things are, or how charged they are and how far away. If they start getting closer or farther or moving around, the information seems to change and the force seems to change accordingly. So we don't literally know how this works. Nobody literally fully knows how this works, but all we know is there are some numbers that describe, and some arrows that describe these objects that seem to be traveling back and forth between the objects and getting updated every time the objects move. Somehow information is being exchanged from one object to the other. I'm not saying we really know how. I'm not saying that it's not sort of crazy to believe in that. I'm saying it's even crazier not to believe in it, because it's happening. It's crazy that it's happening. That's what's crazy. What's crazy is that the earth somehow that a proton can pull on an electron with an exact amount of pull in newtons that's based on where the electron is. Even though the proton's not touching the electron, it somehow knows where the electron is. That's the crazy part. So in order for us to even get our mind around it, or to make predictions, which we can, which work, and make circuits and all of this stuff, we say, okay, fine, that information that somehow is in between the two objects, the information that's being carried back and forth, we're going to call that the field. We're going to, from now on, say, we don't literally know what a field is. I don't literally know what a field is, but I know there's got to be some word to describe some mechanism, some phenomenon, some medium that is occurring between a proton and an electron to exchange the data back and forth between the numbers and the arrows, like the literal, not just numbers, but directions. The electron has to know which way to be pulled or pushed. Somehow it knows. I don't mean knows like this, but I just mean knows operationally. So the field is the word for that mechanism that contains and transmits the information back and forth. I believe in it because it's happening. How do I picture it? Well, first I picture it with these arrows. I picture like an arrow everywhere in space, pulling in to positives and pushing out. I'm sorry, pulling into negatives and pushing out from positives, because the arrows represent to me what would happen to a positive charge if it were there. Now, hold on. There's only 13 minutes left. I do have to get to something here. These questions are great, so I can't resist answering, but let me just scroll through the chat and see what else is going on and see if I can. Okay, wait. Yeah, so Maisha is, if we had one charge, it would create a field that encompasses the entire universe because there are no other charges. Absolutely yes to Maisha's question, John. Just curious, is heat that way? Okay, John's question's totally off topic, but I'm going to say, if I had to choose between, the great crunch is not really believed in anymore. It's not really credible. So if I have to choose, I'm choosing heat death. That's my quick answer to John. I mean, it's a great question. I just can't really go more deep with that right now. But wait, oh my God. Oh, okay, cool. Okay, I'm psyched. Thank you, Maisha. Black holes. Oh my God, I totally do want it. That's a great question about black holes. I'm going to get myself all. Black hole, the fast answer on a black hole is a huge source of gravitation. A black hole is an enormous M somewhere in space that is so incredibly dense, an enormous mass that is, that's so incredibly dense that it takes up a tiny, tiny amount of volume. A black hole is an enormous amount of mass that takes up infinitesimal volume. In other words, there's barely any matter there, but there's huge mass. So yes, gravitationally, it pulls everything in, or pulls things in. Black holes are really cool. I can't get much more into them right now than that. The thing about a black hole is that it has so much mass per, can I say this? All right, just because this is cool. Look, okay, I'll say this quickly because it's worth it, because it's a great question. All these questions are great. We'll somehow get back. You guys, you certainly know how to take me for a temptation ride. It's to your credit, and you deserve it anyway. You deserve to get anything out of class if you can at this point. So Okay, quickly on the black holes, because they are really cool. Regular planets, regular objects in space, stars, what have you, they have a certain amount of mass, they have a certain amount of volume. Like the Earth has a big amount of mass and a finite amount of volume. It is 6 times 10 to the 23rd kilograms of mass. It is like 6.0 times 10 to the 6th meters of radius. Okay. If you want to blast, if you want to blast a rocket ship off from the surface of the moon, of the Earth, right? In order for it to get, how can I say? Okay, you throw something up, right, and it comes back down. Gravity. You throw something, you give something an initial velocity. It goes and goes and goes until it runs out of velocity, and then it comes back down. The entire time, gravity pulling on it, right? So you give something a certain amount of kinetic energy, and it goes until it converts all that kinetic energy in, until it runs out of kinetic energy, it converts it all into potential energy, and then it comes back down, right? Or it's a normal just throwing something up on the surface of the Earth. If you think about it, of course, the faster you throw something up, the higher it can get before it starts coming back down, right? I mean, you shoot a gun with a muzzle speed of like 200 meters per second. The bullet's going so fast at the beginning that it takes a really long, it has so much kinetic energy at the beginning that it takes a really, really high trajectory. It really achieves a very high height before it runs out of all that kinetic energy and turns it all into potential energy and starts coming down, right? So all I'm saying so far is with regular objects on a regular planet, the faster you shoot it up, the higher it will get, or in other words, the farther away it will get before gravity returns it to its origin. Now, the whole time gravity's working, right? Gravity's pulling down on something the whole time. It's just that originally, so it's losing speed the whole time it's going up, but it starts with speed. So it takes a while. It's continuous. It takes a while for it to lose all that speed before it gets to a certain height. Why is it losing speed? Because it's decelerating. Why it's accelerating negatively. Why is it accelerating negatively? Because of the force of gravity, right? Okay, that's just like normal stuff. Here's like the little catch though. If you're following everything I'm saying about GMM over R, now this is worth hearing, all of you, like as long as someone's asked. Again, you may understand a lot more and think it's more interesting when you hear what I'm about to say, and you will follow it. It's not what I was intending to say today, but it is a very worthwhile thing to think about and hear. As we go up, we lose velocity due to the downward pointing acceleration of gravity, due to the downward pointing force of gravity. Okay, but now that we're all understanding that gravity, strictly speaking, is a force that is GMM over R squared, strictly speaking, the force of gravity is inversely proportional to the square of the distance between two objects, right? That means that as you start getting high enough, right, the force of gravity starts, as you start getting higher and higher, the force of gravity starts actually getting weaker and weaker, right? As you go higher, you lose speed, but you lose speed. This goes back to like our original things with the springs and everything. We used to always say that gravity is like always 9.8 meters per second squared. We used to treat it like you lose 9.8 meters per second of velocity every second as you're going up. And we would treat it like you're gaining 9.8 meters per second of velocity every second that you're falling down. And that's approximately reasonably true if you're not moving that much, if you're basically at the surface of the Earth. Approximately, if your R isn't changing that much compared to the whole radius of the Earth, compared to how far you are from the center of the Earth, if you're, we're like 6 million meters from the center of the Earth. So if something gets thrown up like a meter, that barely makes a difference in how far away it is from the Earth. So it barely makes a difference in the 9.8 number. So basically a thing loses 9.8 meters per second every second as it's going up. But if you shoot something high enough, if you give it enough speed, we've never said this before, but I'm saying it now, if you really are looking at these equations and following them, then as something goes higher and higher, it continues to lose speed. It continues to accelerate negatively due to the continually present force of gravity. But that force gets weaker and weaker as you get higher and higher, if you're really being correct about it. As you get significantly higher, like higher than the Empire State Building, higher than Mount Everest, whatever, as you're getting into the Earth's atmospheres, you're getting higher and higher away. You're losing speed, but not always at the same rate, at a lesser and lesser rate. Like first you're losing it at like 9.8 meters per second every second. Then you're losing it at like 9.7. Then as you get higher, it's like 9.6, then 9.5, then, right? So if we could give something enough speed, if we started something with enough, so things still, what goes up still must come down. And I'm still saying that gravity from the Earth still, no matter how high you get, there's still going to be some gravity, no matter how far out you are. There will be some pull down, even if it's like 0.00001 meters per second every second. No matter how high away you get, there's still some pull down. But if we could give something enough initial speed that basically the rate at which it was going up was faster than the rate at which it was losing speed. I mean, that's, you can't really compare those two things directly the way I'm making it sound, but basically if we give something a good enough head start, then it would take it, then it'd be like Zeno's paradox. If we give something enough initial speed, then no matter how high it gets, even though it's still losing speed, it's going to lose speed at a lower and lower rate. So say it's all the way this high and only has like 1 meter per second of speed to lose before it like now gets to zero and start falling down. Well, in like a half a second, it'll lose a half a meter per second of speed. So now it's at a half a meter per second, right? But now it's higher. So it's losing things at a slower rate. So now in order to lose that half meter per second of speed, it's going to take more than a half a second. Like in the next half second, it's only going to lose like a quarter of a meter per second, right? This is like Zeno's paradox, if you've ever heard of that. If we could choose something fast enough, in other words, it would get to the point where no matter what rate it was losing speed, it was still going up faster than that rate. So it would never fall back down. We can shoot something fast enough at something called escape velocity so that it can supposedly escape the clutches of Earth's gravity. Even though gravity extends out forever, you can shoot something fast enough that by the time it would fall down, it's already too late and it won't fall down. It'll be outside of Earth's gravitational field, effectively, not literally, but for all practical purposes. That's called escape velocity. So we can shoot rockets that make it to the moon. The escape velocity of a rocket. Okay, I'm just answering this question now. We're going to end in 3 minutes and we'll get back to the diagrams on Wednesday. I would encourage you, if you're at all confused or whatever, by the way, please, to be honest, I got through all the diagrams in the other class. This is too cool to not be worth it. But I got through all the diagrams in the other class. So if you care or you're nervous, you can watch, when I post the YouTubes, you can watch YouTube from the other section, and then they'll have to watch yours so they can see this cool discussion. Well, it'll all come out in the wash eventually. But if you're nervous or whatever and want to know before Wednesday how the diagrams work, you can watch the other video. But with the 2 minutes left, I'm going to finish this question because it's now here's what I'm doing and it's just too cool not to. And I'm almost there. But I'm saying, if you shoot a rocket ship at about 45,000 miles an hour, like that's a real number, okay? For approximately 45,000 miles per hour is escape velocity from Earth. It's a number that's calculated based on Earth's mass and Earth's radius. It's a finite number. If we shoot rocket ships at greater than that speed, they in effect don't fall down, right? So they can make it to places like the moon. It's called escape velocity. To escape from Jupiter, we would need even more velocity because Jupiter's even more massive per its volume, but it does have such a number associated with it. Here's where I'm going with all of this. The escape velocity for any one given planet or star, or whatever, is based on how much mass it has per how much volume. Like the more mass it has, and the more volume, the more mass it has, the higher number you have to reach to escape, and the greater and the lower the volume it is, the harder it is to escape. Well, what a black hole, okay, so escape velocity is a finite number for any finitely dense object in the universe. Any star you can imagine, any planet you can imagine, there's some number that if you were to go that fast, whether or not you had the technology, If you were to blast something that fast and you could get off that planet or that star, you could effectively escape its gravitational field effectively. Okay, that's what escape velocity is. What does this have to do with black holes or Elizabeth's questions or whatever? Here's what, and I know there's 0 minutes left. What a black hole is something that has so much mass for such little volume that the escape velocity for that situation is greater than the speed of light. A black hole is something that is so dense, it's so massive, but so not voluminous, so tiny in space that even light is not going fast enough to escape it. Therefore, neither light nor anything else can escape it. Therefore, it's black. And therefore, it sucks everything in because it's so incredibly dense that we can't outrun gravity trying to run away from it. I don't know if that makes sense or not, but it's a great question. I know there were other great questions in the chat. So, yeah, the more volume, the more velocity. No, the less volume, the more velocity we need. Okay, so okay, you are the cool class. Okay, yes, and the side facing the moon is high tide on the other side. Yes, that's right. Okay, and thank you for the homework. Okay, sorry. Okay. Okay, so sorry. I don't know if that was good or bad, if that did anything for anybody, but it's true. And those were great questions. And thank you for paying so much attention. And we'll get back to the diagrams on Wednesday. And there's certainly no new homework, obviously. I just owe you a million things, including grades that will be high. Okay, thank you very much, all of you. Goodbye. I'm turning off the recording.